Okay, so for Chapter 8, Objective 3, we are going to be looking at two more tests. So we already had geometric and nth term test, and then today we're going to be looking at the integral test and the p-series test. So just a reminder, like what we're doing here for the first 4 sections, I think it is, we are just going to be learning a bunch of different tests to determine if an infinite series, does it converge or does it diverge? And so far, the different tests that we have that we're working with is we did geometric, right? So if the ratio is less than 1, our series will converge, and that's because the terms will be getting smaller and smaller. Our other one that we did was the nth term test, and that didn't help us decide if something converged. It only decided if it diverged, right? So geometric told us if it converged or diverged. Nth term test only determines if it diverges, and that was if the tail end terms do not go to 0, then it will diverge. If it does go to 0, who knows? And then we also looked at a sequence of partial sums, which helps us to determine convergence and divergence as well. It's not really a test, it's more of an investigation. And then now our latest ones are going to be p-series and integral. So we're going to start with our p-series test though first. So for a p-series, in order for it to be a p-series, it has to take on this form right here. So 1 over n to the power of p, okay? So p will be the number value. So p will be some sort of constant, okay? So p will be a number value or a constant, and then n will be the variable. So other forms, though, that you might want to make sure that you recognize, because, you can always play with things. They don't have to look exactly the same, is that it might look like something like n to the negative p. Like that still would be a p-series, but you would always want to rewrite it into this format here. Excuse me. Okay. And then we have a special kind of p-series, which is what we call harmonic series, and this will pop up quite a bit. So we're going to want to be familiar with not just what we call the p-series, but the specific one, which is when the power is equal to 1. And so we will refer to that as the harmonic series. And I might occasionally say, oh, and it's a p-series with a power equaling to 1. But our harmonic series is just when the power is equal to 1. And so when we let n equal 1, we would get 1 over 1, which is 1. And then if we let n equal 2, we would get 1 over 2, equal 3, 1 over 3, and so on until we get to, if we ever get to, infinity. So now that we know the p-series, so now when will it converge? When will it diverge? So what are the rules for the convergence of a p-series? So the rules say that it will converge if your power is greater than 1, and then it will diverge if your power is between 0 and 1. So if it is negative, like if it's a negative power, it will automatically diverge, but it's not a p-series, right? So for example, let's say that we had something like 1 over n to the negative 2. That would just be n squared, which would diverge by the nth term test, right? So we would do the limit as n goes to infinity, say, of n squared. That would be infinity, which is not 0, so would diverge. Okay, so but this is not, we would not call this a p-series though, okay? So that's why that is not taking into account your negative powers. So if the power is greater than 1, then you will have a converging series. If it's somewhere between 0 and 1, including 1, then it would diverge. So that means the harmonic series automatically diverges because its power is equal to 1, and so it falls into this category here. And so not that you can memorize, of course, memorizing is fabulous, but understanding is more fabulous. So why is that? Why is that? So we're going to just take a look at just kind of like the denominator component. So if we have 1 over n versus 1 over n squared, 1 over the square root of n, because that would be, the n to the 1/2 power. So if I were to graph the denominator only, so if I look at just the denominator, what is the graph of n equals our x, right? If you think that is. So that graph is linear, right? Looks something like that. And then what about the denominator here? What does the graph of n squared look like? So, well, that's parabolic. And then what does a graph of the square root of n look like? And that's the radical graph. So what is happening here? This goes back to that nth term test where the tail end terms, if they go to 0, it may or may not converge. So what is happening here is all of these tail end terms would go to 0. However, they would not all grow quick enough. So if I look at n, it has no concavity, right? So that secondary would be 0. So its rate is not increasing. Whereas over here, the n squared graph, it is concave up, right? Concave up, its rate is increasing. Whereas if we take a look at the square root of n, it is concave down, its rate is decreasing. So the rate of growth is decreasing, the rate of growth is increasing, and then there is no rate, right? So the second derivative would be 0, right? So its rate of increasing, decreasing would be 0. So this would be a situation where the tail end terms, all three are going to 0. However, this is the only one that will converge because it is the only one whose denominator is concave up, meaning its rate of growth is increasing quick enough for us to have a convergence. Whereas over here, that yes, that denominator is growing. Yes, the tail end terms are going to 0, but it is pathetically slow because it is concave down. So yes, it's increasing, but that rate of increase is not there, right? So yes, the y values are going up in value. However, it's going too slow, concave down. Okay, so that is the why behind it. Okay, so that's why that power needs to be greater than 1, so we get that concave up growth to get those terms to drop to 0 quick enough. Okay, so here we go. We want to know, does the series converge or diverge? So when we're looking at this, we look at the power, right? So for this particular problem, the power is 5/3. And then we determine that that is greater than 1. So because it's a power greater than 1, then this would be a series this would be an infinite series, forget the word infinite, that converges. So that would be just following the rules, right? Okay, so let's take a look at this next one here. So for this one, it's not written into an infinite series, so we're going to do that ourselves. So when we look at here, so what we're looking for is a pattern. So I can see that 2 is being squared, 3 is squared, 4 is squared. So I'm going to rewrite this one as to follow that kind of same vision, right? So I'm just going to rewrite it as the cube root of 1 squared. And I can do that, right? I'm allowed to do that. Let me zoom in here just a little bit. And so when I do that, I can see that pattern better. So it looks like the numerator is always 1. It looks like we have a cube root always. And then we're taking each of the numbers 1, 2, 3, 4. So each of our integers and we're squaring it. So each of our integers and we're squaring it. And we are starting at the integer of 1 and then the dot, dot, dot going to infinity. So then this is, all I did was take that rewritten or that expanded form into summation notation. And so from there, I want to go ahead and rewrite it so I can recognize it as that P series. So it will still be that summation from 1 to infinity, and then it will be 1 over n, and then a power of 2 and a root of 3. So put it in from radical form into exponential form. So then when I see that, I can see that the power of this P series is 2/3, which is a value less than 1. So that means if I were to graph into the 2/3, not 1 over into the 2/3, but into the 2/3, I would see that it was concave down. So that means it's got a decreasing rate of growth. And so that's just not good enough. So even though the n terms are going to go to 0, it just isn't going to make it go to 0 quick enough. So therefore, our infinite series would diverge, right? Or just look at the rules above. If the power is less than 1, and less than or equal to 1, and yet greater than 0, the p-series would diverge. Okay, so let's go ahead and take a look at this one here. So again, I'm going to go ahead and do a little rewrite and put it into that format. So only n is to that -2 power, not the 4. So the n squared will go to the denominator. And if you're like, well, that 4 is suspect because according to that p-series, it doesn't have a 4 up there. So you can always pull coefficients out to the front, just like you would with integrals, right? And so if that 4 is ever distracting or confusing, just yank it to the front and then focus on what you have here. So then once you do the rewrite, identify the power. So the power is 2, right? So the power is 2, which is a value greater than 1. So then therefore, that infinite series would converge. And again, that's because n squared, that's a quick enough growing graph that will allow the terms to drop to 0 quick enough, right, in order for the sum to occur, meaning the infinite series would converge. Okay? All right, so let's take a look at the integral test. So for this one here, let me do a little shift. Maybe we'll do a little shift. There we go. Okay. All right, so for the integral test, so this one right here, definitely you are going to want to go back and review your chapter 7, so the improper integrals, because that's what this whole thing is all about, improper integrals, and then seeing if that converges or diverges. So what the integral test says is if you have a positive, continuous, and decreasing function for x greater than or equal to 1, and that's assuming that your index is at 1, but if it isn't, if it's at like 2, 3, 4, 5, like that's fine too, this still would apply. Okay, and then we're going to have our rule and just be equal to function form. So that way, instead of integer values being domain only, which is this one right here, we can look at it into function form as well. Okay, so if the improper integral converges, the infinite series would converge as well. If the improper integral diverges, the infinite series would diverge as well. So that's what this is saying. So they either both converge or they both diverge. And so what we would do is we would have to put it into that integral format and then see from there, excuse me, see from there if the improper integral diverges, my series diverges. If it converges, my series converges. Okay. So then our first step here is we want to rewrite that into an improper integral. So that is kind of our first step. So our index or our lower limit would be 1, and then our upper limit would be infinity. And then we're going to put this into function notation. So everywhere I see, an n, I'm going to rewrite that as an x term, and I'm going to put that as -1/2x dx. And then because it is an improper integral, I need to rewrite it as a limit. So that will be b approaching infinity. And then I can see that I have integration by parts because I have, just x and then a transcendental, so x and e to the -1/2x. So I'm going to let u equal x, and then that derivative is 1 dx, right? So this is a fabulous review from chapter 7. And so dv would be -1/2x. And then when I integrate that, I would get -2 e to the -1/2x. And that would be because on integration of that, I would need to let u equal, chain rule, u equal -1/2x, and then du would be -1/2 dx, which we don't have. I don't even have a dx, do I? And so I would have to multiply the -2 over, and that's where that came from. Okay, so then now let's go ahead and integrate this. So then this would be equal to, I would have the limit as b approaches infinity, and then I'm going to bracket this off here. So I would do u times v, so multiply those two together. So that would be -2x e to the -1/2x from 1 to b, and then minus the integral of v du. So multiply these two together. So I have a double negative, so that would be a plus 2. And then e to the negative 1/2 x dx, and from 1 to b. And then that whole thing is going to be the limit, right? So let me just do an extra set of notation there. All right, so then I'm going to go ahead and substitute in b and 1. And when I do that, because this is a negative, I'm going to move that to the denominator. So replace x with b, so that would be negative 2b, and then drop this to the denominator. So that would be e to the 1/2 of b, and now minus, and now substitute in 1. So I would have negative 2 times 1. And then again, I'm dropping the e term to the denominator. So that would be e to the 1/2 times 1. And then I will have to take that limit. And then now I have plus, and then 2, and then I'm going to integrate that. So e to the negative 1/2 x. So I've already done that integral up here, so I don't need to do that again. So then that would be negative 2 e to the negative 1/2 x, and then integrating from 1 to b. And I'm going to have negative 2 and 2 pull out to the front just to make that a little easier. All right, so keep on, right? So we'll be taking that limit. And I will take the limit at the very end there. And then this double negative is a positive, so that would be 2e to the 1/2. And then I have a double negative there, so that would be minus 4. Evaluate this at b. So again, it has a negative power, so I'm going to move that to the denominator, so that would be 1/2 b, and then minus, and then evaluate it at 1, so e to the 1/2. So something that looks like that. All right, so then as far as the limits go, so this first one I'm going to have to do L'Hopital's, right? Because if I evaluate this, I would have infinity over infinity, so I'll have to do L'Hopital's there. This one, as the denominator goes to infinity, right? So that's going to go to infinity. The whole thing then will go to 0. So that limit will be 0. And then that's a constant and a constant. So then over here off to the side, I'm just going to do a little bit of L'Hopital's. So I have an form of infinity over infinity. So then L'Hopital's applies. So I'll just do that. Therefore, LH. Okay. So that derivative on the numerator would be negative 2. And then on the denominator, it would be e to the 1/2 b, and then times the derivative of the power, which would be 1/2. And then that limit. So the denominator would approach infinity, which means the whole fraction would approach 0. So then that means this goes to 0 as well. And if you think about it, the denominator, e to the x, right, compared to the linear, so just like as an afterthought. So the negative 2b, so whatever that graph looks like, something like that, versus the graph of exponential. So I can see that exponential is like whoosh, growing drastically. So the denominator is going to grow way quicker. So that makes sense that that would go to 0. And so whatever this is equal to, so let me see here, what does that equal? We have 2 e to the 1/2, and then negative 4 times negative 1. So what is that? Positive 4 e to the 1/2. So whatever that is, it's a constant value, right? So it's a constant value. So the integral converges. And then because the integral converges, then I can make the conclusion that the infinite series, because it has to act the same way, converges as well. So because we got a finite value for that integral, that means that the integral converges, which means that the infinite series would as well. Okay, last one here. So for this one, again, dang it, this one's not written in summation notation, so we have to do that for ourselves. So I know the numerator is always 1. And then for the denominator, I can see that it's arithmetic, meaning we are adding 2 every time. So because it's arithmetic, so just a reminder, from 2 or 3 years ago, many moons ago is my point, the arithmetic looks like a linear graph, right? So it would be something like, your mx plus b, so to speak. And so m is the amount you increase by, right? Your slope. So in this case, I'm increasing by 2, so that would be 2n. But I didn't start at 2, I started at 3, so it's a shift up of 1, so it'd be 2n plus 1. And if you're like, ooh, that's kind of magical, how'd that happen? So it's just we're increasing the growth by 2, so that's your slope, so 2n. And then if I were to let n equal 1, I would get 2 times 1, but I didn't start at 2, I started at 3, so I need another increase of 1. So that's the vertical shift of 1. And if I were to check it again, let n equal 2, 2 times 2 is 4, plus 1 is, hey, look, it's 5. And then if I let n equal 3, 2 times 3 is 6, plus 1, and hey, look, it's 7. Okay, so there's enough of that drama. I guess that's not drama. I was being a little dramatic. Okay, so there is my equation, right? I want to do, or my infinite series, I want to do integral test. So for the integral test, right? Not our fan, but that's okay. It's excellent practice for our chapter 7. So we're going to go from 1 to b, and I'm just going to go straight into the limit here. And then instead of 2n plus 1, I'm going to write it as 2x plus 1 dx. So I'm going to go ahead and do a rewrite. So that will be 2x plus 1, and I'll make that to the negative 1 power. And then I'll let u equal 2x plus 1. Du would be 2 dx. And then divide by 2. So I would have 1/2 du is equal to dx. And so this would end up being u to the negative 1, which is just natural log, right? So I'm going to go ahead. And so I have that 1/2 out front. And then I'm not going to find like the new limits because when I do my rewrite, I'm going to go ahead and just make sure that I do that substitution at the same time. Okay, so that 1/2. So the integral of u to the negative 1 is natural log of u, but u was 2x plus 1. And then I'm going to put those limits back on, so from 1 to b. And then let's go ahead and substitute in my upper and lower limits. And then minus, substitute in your lower limit, 2 plus 1. And let me group that out, so because that 1/2 is for both. So then as b approaches infinity, so the natural log graph, just a reminder what that looks like, does something like this, right? It's creeping up to infinity as you approach infinity. And so that means this is going to infinity, which means that the integral is going to diverge, right? So the improper integral will diverge because it's approaching infinity. And so because the improper integral diverges, that means the infinite series diverges as well. And that is that, people. That is that. So there is 2 more tests.